Hello AP Chemistry, and welcome to Chapter 5, an Introduction to Thermochemistry, which is going to go hand in hand with Chapter 19, and we will do them together. You will find that some of the things that we talk about are beyond the scope of the actual AP curriculum, so you will find that those things are emphasized less, right? Even though they're in your book and they are part of your outline, right? Because these are things to know and they do help to finish out the picture. But if it's not emphasized either in the WebAssign or in the EP or anywhere in our class discussion, then there's a strong possibility that that stuff is beyond the scope of the AP curriculum. All right, so thermochemistry. So it starts with a refresher on the concept of energy, right? It does give you the equation for average kinetic energy, which we talked about the concept last year when we said that the temperature in Kelvin is directly proportional to the average kinetic energy of my particles, right? And here's the equation for that. You also learn in middle school about the concept that we have potential energy and we have kinetic energy, and we have a lot of types of potential and we have a lot of types of kinetic, right? And that there is interconversion between the two because, dun dun dun, right, energy is conserved, right? So anyway, Ke equals 1/2 mv squared, right? That's an equation that you should know. And note that this is Ke average, right? So this is not necessarily the energy of a particular thing. We are saying typically this is applied to a bulk group of particles, right? And the average kinetic energy is going to be equal to 1/2 of mass times the velocity squared, right? Which does go back to some of the stuff we talked about last year when we said that if Ke average is related to the kinetic energy, it's related to temperature, right? If something has a higher temperature, right, we have two batches of molecules at, say, the same temperature, then we can maybe start to draw distinctions between their respective masses and velocities, right? Something to tuck away from when we get to that unit. Here, this is electrical potential energy, right, which has to do with this figure over here, where potential energy, right, so kinetic energy being the energy that relates to moving things, right, whereas potential energy is based on location or proximity, right? And so this diagram, so keep this equation in mind because we reference that again multiple times in the next unit. This is a different form of it. But what it talks about is the fact that we have these charges, right? So this is charge particle 1. And this is charged particle 2. And what it says is that these two particles, if they are infinitely far apart, their respective energy is approximately 0, right? In that there is no attraction, no repulsion, so no energy between them, right? But as those particles get closer and closer, because we're basically reading this graph in the opposite direction, right? As those particles get closer and closer, if they are oppositely charged, eventually we reach a point where their proximity makes them attracted to each other and they will tend to stick together, and that's where you would say, that's where we form a bond, right? If they happen to have like charges, then forcing them closer and closer together, you'll see, gets us higher energy, and that energy needs to be put in to put them close together because they experience strong repulsion, right? But anyway, types of energy, right? Which then leads us to types of systems, right? And it's going to be very important that every time you answer a free response question, that we always think about what is my system and what is my surroundings, right? System's always going to be the thing that we're focused on, the thing that we're trying to talk about, and the surroundings is everything else, right? If you're ever not sure, if you're ever addressing a question and you're not sure, then define it for yourself, right? Define it on your, like in your answer, right? The system is blank. And the surroundings are blank, right? So that way you can then frame your answer from that perspective, okay? But anyway, we have types of systems, right? Most of the time we are going to be talking about this, right? Closed systems for our, for most chemistry experiments, right? We have the concept of work, we have the concept of heat, and that overall, that is our energy, and that energy is conserved, right? And this diagram is a great way to show that, right? A battery has a certain amount of energy stored in it based on the chemical components of it, right? Which we'll actually talk about in chapter 20. But one way, if we short circuit the battery, right, and connect one into the other, right, we can lose all the energy from that battery as heat, right? Which is actually part of how, like, if you've ever seen those videos, like, survival videos, where you can take a 9-volt battery and touch both electrodes to some steel wool, right? And then basically you can use that intense heat that comes off of there, right, from basically connecting two ends and getting the large flow of electrons. That intense heat can then expedite the oxidation of the iron in steel wool, right? And basically you can use that to start a fire effectively, right? Alternatively, right, we could use that battery plugged into something to do some actual work, right? To move something, right? Which is what work means, right? We are moving something against a force and across a distance, right? And then some of it will be lost as heat, but the total amount of energy is limited by the chemical components of the battery, right? Conservation of energy. Here are your sign conventions. Make sure you know them. And in general, they're always the same. So if you stop and think about it, here is my system. Is it going out of my system? Then it's negative. If it's going into my system, then it's positive, right? And so if you always stop and think about that, that helps. 5.3, the basic point here, right, is 1, the atmospheric pressure is essentially constant, right? So for most of the experiments that we will do, right, if you think about like a beaker or a flask or something, right, it's open to the atmosphere. And even if we were to say put a lid on it, right, it is still subject to the atmosphere because we're not getting like this tight seal with the production of gases or the consumption of gases such that the pressure inside would change, right? So because the pressure of the atmosphere doesn't change considerably during the course of a normal chemistry experiment, we can say that anything open to the atmosphere is under constant pressure. And as long as our experiment is done at constant pressure, we can say that the heat measured at constant pressure is equal to the enthalpy, right? Your book goes through the derivation, but basically the concept of work cancels itself out when we put our heat and our enthalpy and energy equations together, and those two things are equivalent, right? So again, 5.1 through 5.3, at this point in time, the takeaway point is that as long as we are at constant pressure, which as long as it's open to the atmosphere, is constant pressure because the pressure of the atmosphere doesn't change considerably during the course of a normal chemistry experiment, then enthalpy equals heat. So over the rest of this unit, as we talk about enthalpy, enthalpy is a reflection of the heat. Yes, the thermal energy that is exchanged. Yes? All right, those are the takeaways as we dive into the rest of this unit where we talk about how to experimentally determine heat and enthalpy, how to calculate enthalpy using different types of information. All right, thank you for listening. Be good, and I will see you soon. Bye.